Hello, my name is Ifeanyi Roland Onyoaku, and today I'll be doing my presentation on my progress report for Malthus's population model with disease death rate consideration. Now, what's the purpose of this experiment? This is literally, we did a review on Singh's Malthus population model with disease. We did a review on his papers called Study of Mathematical Models for Thomas R. Malthus's model paper. And hence we found a couple of issues, but let's break it down. First of all, he discussed that about three different ways of predicting population size, which is Malthus model, logistic model, and coalition model. And of course, he listed some factors for Malthus's model technique, which is what we're focusing in. Of course, man must survive. Man must eat to survive. Rate of population growth is higher than food production rate. There are consequences of these rates that must be kept equal due to balance, and of course, decrease in population due to famine, disease, poverty, and war. However, when he implemented his model, he only put into consideration time and relative growth rate. He did not put into consideration the famine, diseases, and all. So then for our solution to this model is like, hey, let us introduce a parameter, for instance, disease-induced death rate. However, we could go more, but because of our time constraint and when it would take to implement this, we stuck to this. What method did we choose to use? The software we chose to use is NetLogo because of this is a great tool which I've learned in this class. The agents we chose is the reproduce humans agent and the check death rates agent. Reproduce humans agent will deal with the relative growth rate which Singh already put in his paper. And why check death rate would introduce the parameter for disease-induced death rates. The assumptions for these models are each tick in NetLogo will represent a year, and we want to keep this to 10 ticks, maximum of 10 ticks, which is um, maximum of 10 ticks, which would be a span of 10 years. And of course, the initial population size would be that of 2010 because we want to use the data from US Census Bureau. And of course, the disease-induced death rate will be generated from data which we will get from the CDC. And of course, the disease also induced can be introduced in a year, 2 years, 3 years span, depending on how we want to run the simulation. Now, how do we want to go about this? The actions, there are three main actions. We run the simulations, we validate the results, and we verify the results we get. Now, when you say the simulations, we want to run three different simulations, which is input disease death rate, which is introduced in every 3 years. This is disrupts the population growth, or every 2 years, or let's say every year. We want to run these three simulations and see how the data would match with the real data. Now, verification. Of course, when we start building this model, we want to verify how it matches with the implementation of the formula for the model which Singh introduced in the paper. And hence, when we run this model without disease death rate, we will compare and we'll use India's population since that was what was used in paper. We'll compare what we get from the model to what he has on the paper. If it matches, then our model is verified. To validate our model's changes or the changes which we added is that we'll run for the US population with these three simulations listed and compare with the actual real population size over the past 10 years. And the closer it is to the actual population, that validates our model. And we can compare with what we would have without the disease death rate in the model. And that should tell us, hey, which is better. Now we'll go through a short demo, and which is so setup. We we have human population 100. This is just like sample of what I've already built. So you can see right now it just increases by time by 2 multiplied. It increased by 2 like 100, 200, 400, 800. So but we still have more. We will have to add to it. Okay. So the code we still have reproduce humans. We're still yet to put the Malthus formula, which increases as listed in the paper. And then we have the check death rate, which is also the placeholder for the introduction of disease death rate. Yeah, what else to do? As you've seen, we need to implement the Malthus formula, as you saw, and then we need to also get the disease rate from CDC sites, and that's what we'll introduce. Run simulations as described above, the real simulations, and then verify and validate the results. This is the end of my, sorry, it seems rushed, but I needed to finish on time. Thank you so much.